Welcome everyone to this week's Autonomy Talk. This week is a pleasure to have with us Professor Tobia Marcucci, who is an assistant professor in the Department of Electrical and Computer Engineering at the University of California, Santa Barbara, where he's also affiliated with the Department of Mechanical Engineering and the Center for Control, Dynamical Systems and Computation at Santa Barbara.
Pablo's talks.
So first of all, Tobia is not new to us, right? He received a PhD in computer science from the Massachusetts Institute of Technology, working with Russ and Pablo. And before joining UC Santa Barbara, I spent some time at Amazon as a postdoctoral scientist. Actually, if I remember correctly from one of Russ' presentations, implementing some of the ideas that he's gonna talk about today. His research lies at the intersection of convex and combinatorial optimization with applications to robotics, motion planning, and optimal control. And during his PhD, among other things, he developed this toolbox for graphs of convex sets, which is finding a lot of application and is being kind of disruptive, so to say, in some domains. And I think Tobia thought of giving a tutorial today, which is great, and I look forward to learning more about it. Feel free to ask questions during the talk. We will also have a session after the talk. But without further ado, Tobia, thanks again for agreeing to give a talk and looking forward to it.
Well, thank you so much, Joelle, for inviting me. Just to double check, can you guys see my cursor on the screen if I move it around so that I'm not pointing to the empty space?
Yes.
Perfect. Okay, well, again, thank you so much for inviting me. I'm very excited to give this presentation. As Joelle said, I will try to give a high-level tutorial on this new optimization framework that I've developed during my PhD and I'm still working on, which is called Graphs of Convex Sets. This is an optimization framework with a variety of applications. We will see mostly robotics applications, some maybe control, but it's broadly applicable in decision-making. So this is the outline of my presentation today. And by the way, feel free to ask questions at any time if something is unclear, in the spirit of making it a tutorial. If it turns out to be interactive, I think it's more exciting. But yeah, this is the outline of my presentation today. I will start with some motivations and goals. Then I will describe what these graphs of convex sets are, these mathematical objects, what kind of problems can we pose over a graph of convex sets, and how can we solve these problems. Then I will go through a variety of examples, from simple more toy examples to kind of real-world applications and some hardware experiments. If the time allows, at the end, I would like to give you a crash course on this simple Python library, GCSOPT, that I've written for solving GCS problems. Ideally, this should make it very straightforward to code and solve a GCS problem, and maybe you can also integrate it in your research. So what made us starting working on this kind of research direction is a simple observation. Is the observation that at the core of many robotics problems is the need to simultaneously optimize high-level discrete decisions and low-level continuous decisions. So integrating high-level discrete logic with low-level continuous control. If you think about this interaction between discrete and continuous decision-making appears essentially everywhere in robotics. If you think of the famous video of the Atlas robot by Boston Dynamics doing parkour, that's an example of a problem where you have this interaction. The robot that is facing a parkour course has to make some high-level discrete decisions, for example, the sequence of obstacles that the robot is going to face, but these high-level decisions need to be optimized jointly with the low-level continuous trajectories of the center of mass, for example, and the limbs of the robot. If you think of robot manipulation, again, you often have this interaction between discrete and continuous. Typically, we want to manipulate the position and orientation of objects, which is naturally a continuous goal to achieve, but we have to make discrete decisions along the way. Making and breaking contacts is the simplest decision, but you can think of a robot having to reach an object that is too far away from the robot, so the robot can decide to grasp another object, in this case, something that looks like an hammer, to kind of pull the objects toward the base of the robot. And grasping or not grasping, using or not using an object is typically a Boolean decision that needs to be optimized jointly with the position of the object that you want to grasp. If you think, for example, of UAV trajectory optimization in presence of obstacles, again, you have this interaction between discrete and continuous decision making. If the UAV is facing a tree, it has to make a Boolean decision again, do I go left or right of a tree? But at the same time, it needs to optimize the continuous trajectory of the center of mass in order to make sure that this discrete decision of which side to move with respect to the obstacle is actually feasible given the robot dynamics. And these kind of interactions also appear all the time in industrial robotics, in more like robotics warehouses. For example, when I was working at Amazon, we worked a lot on problems of minimum time pick and place, and there you have discrete object sorting and bin packing problems that need to be solved simultaneously with trajectory optimization problems. So if you look at the state of the art, of course, or at the literature, of course, we are not the first people that think about this interaction between discrete and continuous decision making, right? And depending on the field that you come from, you might be familiar with different incarnations of this interaction between discrete and continuous. If you come from control theory, you might be familiar with hybrid dynamical systems, which are the dynamical systems that exhibit both discrete and continuous behaviors. This field of hybrid dynamical systems lies the rigorous mathematical foundations to study concepts like stability, reachability for this kind of systems. But often the models, the equations that result in this kind of analysis are too fine-grained, are too detailed for the kind of problems we care about in robotics. If you think about modeling the Atlas robot doing parkour as a dynamical system, you would get a very complicated model which is not amenable to efficient optimization algorithms. If you come from robotics, you might say, well, but this is really what task and motion planning has been developed for. And in fact, in task and motion planning, there have been hugely scalable techniques for these kind of problems that involve discrete logic and planning. One issue with that is that TAMP, task and motion planning, doesn't really lead to a unified mathematical formulation of these problems. Therefore, it makes it hard to study these problems formally and analyze their complexity and also use our strongest optimization algorithms against them. Finally, if you come from optimization, we say, well, certainly this is going to be a mixed integer optimization problem. And you would be essentially right. The issue, again, is that mixed integer optimization is too low level as a language for most roboticists. You cannot think that engineers at Boston Dynamics can directly transcribe the problem of doing parkour with Atlas as a mixed integer problem. So the goal for us has been to try to develop a modeling and computational framework that kind of fills these holes. First of all, this framework must capture the essence of our problems, in particular, this interaction with the high-level discrete skeleton of these problems that we have described before, and the interaction with the low-level continuous details. And ideally, it also leads to very precise and neat mathematical problem formulations that we can study formally. Ideally, it's also optimization-friendly and leverages our most powerful tools from combinatorial and convex optimization. There have been decades of results that we would like to take advantage of in order to design efficient optimization algorithms for these problems. And finally, it must be easy to use. We cannot expect that every user of our toolbox is an expert in optimization. So in some sense, we want to shield them from the complexity of the underlying optimization techniques that run behind the scenes. And also we want to allow them to model complex problems with many moving pieces in a modular fashion so that the size of the code that an engineer has to write in order to solve these problems doesn't essentially blow up. So our proposal is this idea of graphs of convex sets, and I'm going to explain next what these graphs are. But in the spirit of making it a tutorial and make this presentation accessible to most of the people, let me just spend one slide introducing some jargon that I will use over and over. I'm sure that many of you are already familiar with this, but let me just spell it out for everyone. So we will mostly consider optimization problems of this form, where we have an objective function f that depends on two variables, x and y, and x are continuous decision variables and y are discrete integer decision variables. So we want to select the value of x and y such that f is minimized. And we cannot just pick any value for x and y. We can only pick values for x and y that are within a corresponding constraint set, calligraphic x. Depending on the assumptions that we make on these functions f, on the set x, and on the decision variables, we get different classes, essentially a zoo of optimization problems. The nicest assumption we can make on the objective function f and the constraint set calligraphic x is convexity. You remember that a function is convex if you take any 2 points on the graph of the function and you draw the line connecting them, then the line lies above the function graph, and a set is convex if you take any 2 points and you draw a line, then the line is in the set. So if we assume convexity of the objective function and the constraint set, and the decision variables are only continuous, so we have no integer variables, then we get a convex program, or a convex optimization problem. Convex programs are essentially the best class of optimization problems, since they are always solvable to global optimality with efficient methods like interior point methods, and we can solve problems with tens of thousands of variables and constraints in a fraction of a second. So convex program, if you can reformulate your problem as a convex program, essentially you're done. If we keep the convexity assumption, but we allow some of the variables or all the variables to be discrete, then we get a harder class of optimization problems, integer or mixed integer convex program, depending whether you have all discrete variables or part of them. These are still always solvable to global optimality, but with weaker algorithms like branch and bound, divide and conquer kind of methods that exhibit kind of a worst case runtime that is exponential. So potentially, if the size of the problem grows too much, the runtime will be astronomical. But there is a deep theory about this class of optimization problem that allows you essentially to predict with a fairly good confidence whether your mixed integer program or integer convex program will be efficient. And we will describe this in a second. So again, this can be solved to global optimality sometimes, although the runtimes are long. Then if you drop the convexity assumption, you get all possible shades of non-convex programs. And there are some good non-convex programs that can be solved nicely, but typically, in general, this is the hardest class of optimization problems. They are only solvable to local optimality, and most of the times they are slow, and the solver can even fail, even though a solution exists. So with this kind of vocabulary in place, let me try to give you a quick description of what is a graph of convex sets. The main idea is simple. If you think of modeling the class of problems that we have described before, so locomotion, manipulation, collision avoidance, all these things, graphs are a natural language to try to describe the discrete skeleton of these problems, right? And we have hugely scalable methods for solving optimization problems over graphs. Now with your phone, in a fraction of a second, you can compute the fastest street from San Francisco to New York, and you will be very close to the global optimum. So extremely scalable tools from graph search and graph optimization. On the other hand, we have convex optimization that, as we have just discussed, is essentially a mature technology for solving continuous optimization problems that scales to, again, very high-dimensional problems. And convex optimization nicely captures the low-level continuous details of our robotics problems. So the kind of question we were trying to respond is how can we combine these two frameworks into a unified framework that is also that kind of preserves the efficiency of the two frameworks independently. And the idea is this idea of graphs of convex sets. Let me start from what is an ordinary weighted graph, again, to try to make it the presentation as simple as possible. I'm sure that many of you are familiar with ordinary weighted graphs. They can be directed or indirected. We have a set of vertices, capital V, calligraphic V, and a set of edges, calligraphic E. Every vertex is a dot connected by edges that are straight lines. Every vertex is typically paired in a weighted graph with a cost or a weight, which is a real number that represents the cost of visiting a vertex. And every edge is similarly paired with a weight or a cost, which is again a real number and represents the cost of traveling along the edge. So in a GCS, we do have something that looks like a weighted graph, but where the weights on the vertices and the edges are not fixed scalars, but are functions of underlying continuous variables. In particular, in a GCS, we pair every vertex in the graph with a convex optimization problem. So a convex optimization problem paired with vertex V is going to have three main pieces, as we have described before: a continuous variable, xv, a convex constraint set, calligraphic xv, where the variables need to live. And then we have an objective function that, given the continuous variable xv, returns you the weight or the cost of the vertex. So again, in a GCS, the weights are not constant, but they are functions of these underlying continuous variables that we are allowed to select in order to minimize the cost. Every edge kind of pairs the two convex optimization problems that it connects. So if we have in a GCS an edge that connects a vertex V and a vertex W, then this is going to be paired with a constraint that couples the choice that we can make for the variable xv and the variable xw through a convex set, calligraphic xe. And then we also have an objective function that again tells us how much do we have to pay to traverse a certain edge. And that is not a constant, as in the weighted graph case, but it depends on the decision variables that we have selected for vertex v and vertex w. So please ask me any question if this is clear. I think that if there is one thing that I would like people to understand is this problem formulation, because as a user of GCS, essentially, this is the format in which we require you to state your problem, and then we take it from there to try to solve this problem. Okay, so if there are no questions, the next kind of natural issue that arises is what kind of optimization problems can we solve over a graph of convex sets, right? And the response is that any optimization problem that you can formulate or pose over an ordinary weighted graph, you can also formulate it over a GCS. Let's take, for example, the shortest path problem. So in an ordinary weighted graph here on the top left, we have a source vertex and a target vertex, and we want to find a sequence of edges that essentially brings us from the source to the target, and we want to find not any possible sequence of edges that does that, but the one with minimum total weight. So the one for which the sum of the weights of the edges that we have selected and the vertices that we have selected is minimized. So this is a purely discrete combinatorial optimization problem. If we generalize this problem to the GCS setting, we are still looking for a path, so a possible way of going from the source to the target in this graph. But once we select the path, the cost of that path, the weight of that path is not given. It's not just given by the sum of the weights that are scalar in the original case, but this time in the GCS case, we have also to select the continuous variables that are paired with the vertices along the path. So we have to simultaneously optimize for a path from the source to the target, but then depending on the path that we take through the graph, we activate certain optimization problems on the vertices that we have to, for which we have to select the continuous decision variables that then decide the actual cost of our path. So again, we need to optimize these two things simultaneously. Other classical problems in graph theory, traveling salesman is naturally generalized to GCS and the minimum spanning tree, for example, but also facility location, bipartite matching. Every essentially problem that you can formulate over an ordinary weighted graph can be translated to a GCS version. If we try to be mathematically a bit more precise, we could formulate the problem over an ordinary weighted graph, over the ordinary weighted graph as it's shown here on the top right. So depending on the problem, shortest path, minimum spanning tree, or traveling salesman, we are given a set of admissible subgraphs that I denote as calligraphic H. For example, in the shortest path, this set would contain all the possible paths from the source to the target. And we want to select one of these subgraphs that can be, again, path, tours, spanning trees, etc. We want to select one of these subgraphs that has minimum weight. And the weight of a subgraph is just the sum of the weights of its vertices. So we sum the vertex weights for all the vertices in W, which are the vertices of the subgraph. And we sum the edge weights for all the edges in F, which are the edges of the subgraph. So we want to select in this list the minimum weight subgraph in this list calligraphic H. With this notation, the GCS problem can be formulated as shown on the bottom right. We're still looking for a discrete object, a subgraph that belongs to the given class of admissible subgraphs. But once we fix a subgraph, then we have to optimize the corresponding continuous variables. And the corresponding continuous variables need to satisfy these convex constraints for all the vertices in the subgraph and these convex constraints for all the edges in the subgraph. The cost of a subgraph in a GCS is again given by the sum of the costs of its vertices and edges, but this time again, these costs are not fixed scalars, they are convex functions of the continuous variables. So yeah, this is the problem formulation for a generic GCS problem. So this encompasses shortest path problem in GCS, traveling salesman, spanning tree, facility location, etc., etc. They all kind of can be expressed in this form for certain choices of this set calligraphic H. So yeah, there is a question, I see. Please feel free to ask.
Hi, Tobia. One quick clarification question. So do we allow overlaps between different convex sets from different vertex? And does that change the problem formulation at all?
Yeah, thank you for asking. In reality, yes, we do allow overlap, but in reality, these sets don't even have to live in the same space. In this formulation here, these convex sets can be even in different dimensions. One can be an infinite dimensional object, the other can be a set in 2 dimensions. They can be, they are really distinct objects as long as you can provide you know, some joint constraint and joint cost function that makes sense to couple these two. But yes, the idea is that they can be optimization problems that have nothing to do one with the others.
I see. Thank you.
You're welcome. And nothing changes in this formulation depending on intersection or things like this. Yeah, thank you for asking, and please feel free to ask any other question. So next, I will try to describe quickly how we can solve these GCS problems, but just to keep you interested, let me try to convince you that, you know, the modeling power of GCS is really vast. We have worked, for example, in our lab, when was actually before I joined Russ's lab, there was a lot of work on, for example, footstep planning and mixed integer formulations for these problems. And they used to take minutes to solve in order to optimize the footholds for about like 10-20 footholds for a humanoid robot like Atlas. Now we can solve these problems almost through a convex program in a fraction of a second using GCS. There are cool problems in computational geometry. In this case, for example, we have something that looks like a robot link that is triangulated, and we want to find the set of spheres that cover this robot link and have a minimum volume. This is very useful, for example, for efficient collision avoidance. We have worked a lot on robot motion planning formulations using GCS, and our techniques allow to scale to high-dimensional planning problems. On the top right, you see two Puka arms, so a 14-dimensional configuration space where we can design trajectories pretty efficiently with GCS, or kind of more large-scale problems with for UAVs. Scheduling problems, I will describe this problem later, or even control of certain classes of hybrid system. Here we were applying it for non-prehensile manipulation, but control of piecewise affine systems, for example, can be seen to be a special case of a shortest path in GCS, and actually the best known mixed integer formulations for those problems are recovered as a special case of what I'm going to present next. So now that we have kind of formulated...
Can I ask you a quick question?
Yes, definitely.
So usually, like what we see is for efficiency, computational efficiency, so people move towards a specialized algorithms.
Mm-hmm.
And I appreciate the framework you're presenting is more like a generalization algorithm.
Mm-hmm.
I'm wondering if you could give some intuition about how this generalization also leads to computational efficiency.
Yeah, that's a nice question, I would say. In particular, what happens, I think that when you generalize and you make the mathematical problem much simpler and easily analyzable, you all of a sudden can borrow many strong results that have been developed over time. In particular, for example, I was working on mixed integer optimization for footstep planning looking problems. And when you have all the equations that are together and you try to put them together to form a mixed integer convex program, you're very likely to miss the high-level picture. And the high-level picture is that you're really trying to solve the shortest path in a graph that is not the graph you're typically study in a textbook. But for the shortest path, you have incredibly strong mixed integer programs. In fact, mixed integer programs whose convex approximations are exact. And then if you realize that connection, you can leverage those and then essentially take full advantage of very smart people that have studied this kind of stuff for decades and you know, import all the results in one block. It is true also for the GCS that now we have more maybe efficient ways of writing these problems as mixed integer convex programs. I will describe it in a second. It is also true that then if on top of that we want to develop specialized algorithms for those, then you can further make it more efficient. But I think the big chunk of efficiency that we gain here is by understanding that our problems share some structure with well-known problems, and we can take advantage of what's known about these problems in the optimization literature. I hope this makes sense as a response.
Yep, thank you.
You're welcome. Yeah, so let me just jump ahead and try to describe how we can solve these GCS problems. We have given this table before, so just to set the expectations, right? Ideally, we have said the best class of optimization problems are convex programs, convex optimization problems. Can we solve a GCS problem through a convex program always? The response is unfortunately no. In fact, most GCS problems are computationally hard, NP hard, if you're familiar with the term, and that means that there are computational barriers that prevent us from reformulating them exactly as convex programs. So the next best thing in some sense is to try to formulate them as integer or mixed integer convex programs. And in particular, given that we have both continuous and discrete variables, we will go for the mixed integer version. And if we decide to formulate them as mixed integer convex programs, then what makes an MICP efficient, right? That's the next question that we mentioned before. Well, certainly there are easy things that make a mixed integer convex program efficient. If you have a small number of decision variables, so small n in m, then that's certainly going to be good. And also if your constraints and functions are easily evaluated and cheap to store on a computer, but these are kind of obvious things. The less the less obvious thing it's that strongly affects the efficiency of an MICP is this concept of the convex relaxation, in particularly the tightness of the convex relaxation. So this is our mixed integer convex program on the top, where we have continuous and discrete variables. The objective is convex and the constraint is convex. So everything is nice in this problem, except for the fact that the variables y are discrete. That is what makes the optimization problem difficult. So for a second, we can just pretend that these variables are not discrete, but they are continuous. And this gives us a convex program. This convex program is called the convex relaxation of the original mixed integer program. And it's a relaxation, meaning that its optimal value, it's a lower bound for the optimal value of the original problem. And this is obviously seen because essentially you're just dropping requirements on these variables. When you're allowing your discrete variables to take continuous variables, you're allowing yourself to select your variables from a larger set. Therefore, the minimal value of your objective function can only go down. So we have this kind of cheap convex approximation of our original problem that provides a natural lower bound to the problem. If this lower bound is accurate, is tight, then we say that the convex relaxation is tight. And when this is possible, when this is the case, then the algorithms that are used to solve these mixed integer convex programs, they will typically be very fast. In fact, if this approximation is not just accurate, but is exact, then we can solve our optimization problem through a single shot convex program. Okay, so there are these kind of two things to keep in mind. We want to keep our problems small, not too many variables, not too many constraints, and we want to ensure that their convex relaxation is a good approximation of the original non-convex mixed integer program. Sorry, non-convex because the variables y are discrete. So at the high level, these are the steps that we take in order to formulate our GCS problem as a mixed integer convex program. We start by giving an integer convex formulation of the graph original optimization problem over the weighted graph. Then we extend it to GCS, and we get some non-convex constraints on the way that then we convexify exactly to get our MICP. So all the details here tend to be quite long and technical, and I would need just a whole presentation to describe these three steps. But I would like to try to give you at least some highlights of some tricks that I think are interesting and can be applied in other problems as well. So the first observation is how can we formulate this problem that we have described before, so the purely discrete problem, as an integer convex program, right? So we have described this problem before. We are given a set of admissible subgraphs, calligraphic H. This can be all our paths or our tours, spanning trees, etc. And we want to select a subgraph of minimum total weight. So in this form, the problem is not efficiently solvable yet, right? Because essentially this would require going through all the set, exhaustively through the set calligraphic H, evaluate the cost of every subgraph, and pick the best. And if you think of the problem of Google Map of going from San Francisco to New York, this would require enumerating all the possible streets from San Francisco to New York. It would be an horrible algorithm. So we need a more kind of numerical parameterization of what is a subgraph, right? And the way we do so is pretty straightforward. We use incidence vectors, which are essentially a binary encoding of a subgraph. If we are given a graph with vertices v and edges e, we can parameterize a subgraph of this graph by using binary variables. We have one binary variable in this vector for every vertex and every edge. The binary corresponding to a certain vertex is 1 if the vertex is in the subgraph, and it's 0 otherwise. And similarly for the edges, the binary is 1 if the edge is in the subgraph and 0 otherwise. So for example, you see here on the right a graph with a subgraph shown in green. All the vertices and the edges in the subgraph have binary equal to 1, and all the other binaries are equal to 0. So this is the incidence vector, and we're going to try to optimize over all possible incidence vector instead of all possible subgraphs. So this essentially maps the original problem of going through a list of possible subgraphs into a search in some high-dimensional space where we have one axis for every vertex and one axis for every edge. every admissible subgraph in our list is mapped to a point in this space, in particular, the vertex of the high-dimensional hypercube. And if we now have a nice convex set that essentially separates the admissible incidence vectors, so the incidence vectors that correspond to admissible subgraphs, if we can separate them from the inadmissible ones, then we have an integer convex formulation of the problem. In particular, these sets, calligraphic Y, that determine your possible incidence vectors are very well studied. They can find in ordinary textbooks for combinatorial optimization. They're typically polytopes, so convex sets defined by linear inequalities. So if with this parameterization and given this set that determines the set of admissible incidence vectors, we can formulate our problem in this form. We look for an incidence vector in the corresponding set, calligraphic Y. The incidence vector must have entries that are 0 or 1, and the objective function is now a linear function of our binary variables. The weight of the subgraph is just obtained by summing the product of the weights and the binary variables for all vertices and edges. When the binary is 1, the corresponding weight is added to the objective. When the binary is 0, we get no contribution to the objective function. So, and again, this is a super well-studied class of integer programs. Everything is known about these programs. And for some classes of graph optimization problems, for example, the shortest path problem, actually some of these integer convex programs have actually exact convex relaxation. So if we drop these requirements that the variables are either 0 or 1, we still get an exact solution. So these are the best possible classes, the most efficient classes of optimization. Integer programs, they can be solved to global optimality through a single shot convex program. So this is somehow the ideal starting point, right? Especially if we have these very efficient formulations, we can try to translate them to the GCS setting. And in order to translate to the GCS setting, that's the second kind of step that I want to highlight before going to the numerical results. If we want to translate these efficient formulations that we have for the discrete counterparts of our problem, we want to translate them to the GCS, we need to find a way of using these incidence vectors, so these binary variables, to kind of activate and deactivate the relevant part of the GCS. Essentially, we have our GCS shown here on the left, and depending on the incidence vector, so on the particular subgraph that we select, we need to be able to use these binary variables somehow to ensure that only the convex costs and constraints associated with the subgraph are actually enforced in our optimization problem. I'm just going to show you quickly how you can do that for a single convex set. In particular, we will look at one single vertex, vertex V, and for that vertex, we want that our continuous variable xv is in the set calligraphic xv if the corresponding binary is 1. So if that vertex has been selected in our subgraph, and we want to enforce no constraint if the binary is 0. We can reformulate this logical kind of implication with a single constraint that looks like this. We multiply the binary by the continuous variable on the left and the binary by the convex set on the right. When the binary is 1, on the left we get 1 times the continuous variable, and on the right we get 1 times the convex set. So we get exactly continuous variable in convex set when the binary is 1. When the binary is 0, on the left we get a vector of zeros because we are multiplying 0 by x. And on the right we get 0 times the convex set. 0 times any set is essentially just the origin. So this constraint, when the binary 0, simplifies to 0 lies in the set that contains only the origin, and that's always true. So the constraint is kind of redundant. So this kind of nicely captures this on and off behavior using the binary variables. One extra step that we do is that we reformulate this constraint in this form where we add the variable z that represents the products of x and y. And then we essentially split this constraint into two constraints. The reason why we do so is because now the first constraint is nice and convex. We have a variable that lives in a non-negative variable that multiplies a convex set. The non-negative scaling of a convex set is a convex cone. So this set is convex. While on the right, we have a bilinear surface, which is non-convex, but for which we have essentially good tools in order to essentially reformulate these bilinear products as convexify exactly these bilinear these bilinear constraints, leveraging the fact that one of the variables is binary. So we have developed a method extending existing methods to reformulate this non-convex constraint exactly. That's essentially where the most technical part is. But yes, at the end of the day, after this convexification of these constraints in red, this trick can be repeated for all the constraints and the costs in the GCS, and we get a mixed integer convex program that nicely models our GCS problem. And most of the times, we do have some basic results, but also empirically, you see that if you start with a discrete problem for which you have a very good, efficient integer convex program formulation, for example, the shortest path, then typically our mixed integer convex program preserves the same efficiency. The same is true, for example, also for the minimum spanning tree, which has efficient integer convex programming formulations. So please ask if there are any questions. This was essentially the most technical part of the talk. Now I would like to go through some examples, and actually before going through the examples, I would just like to comfort people by saying, by kind of reiterating the message that all this math that I've shown is taken care of automatically behind the scenes. When somebody wants to use GCS as a tool in their research, what they have to do is they have to kind of analyze their problem, define what is the underlying graph that represents the discrete skeleton of the problem, define the variables that are associated with the vertices, the convex sets, the convex constraints. Then we can receive this GCS, and you can ask us, okay, solve the shortest path from this vertex to this vertex. We're going to do everything automatically behind the scenes using state-of-the-art solvers, etc., etc. Yeah, please ask any questions. Feel free to unmute yourself.
Hi. My question is about defining like f as like the function of these variables. Like if, for example, like the shortest path problem, is there kind of like a standardized way about taking like your original problem and like defining like how do you, I guess, define like a good f in like the GCS domain kind of?
What is f? Like I've used a few f's.
Oh, yeah. So I guess really, I mean both, like both FE and FE as, yeah, like those like cost objective functions.
We will see a few examples. Maybe with an example, things will be more clear. For example, in motion planning, you can represent with f the length of your trajectory, or the integral of some relevant quantity. Maybe now that I go through the examples, it will be more clear.
Okay.
But the idea is that something that the user has to provide that essentially models your problem, right? So if you have, if you have, for example, a motion planning problem where you want to go from point A to point B by traveling the least distance, your function f can measure exactly that, the distance that you travel every time that you move on a straight line or something like this.
Right. So is it, I guess maybe what I was, or part of my question also was like, is it pretty, because in the original formulation before you turn it into a GCS problem, like you'd ideally be capturing a similar objective function, right? So is it pretty straightforward to like map like your original objective into like these like FE and FE?
You mentioned you're referring to these objective?
So like if I think it was actually the next slide there, like when you have oh sorry, maybe when you gave the example of the shortest path, like you have your C and your CV and your CE here. So like it, I guess taking that, obviously like F and X, like these aren't fixed values like you'd mentioned previously in the GCS framework, as opposed to these like C's being fixed. But I don't know, maybe yeah, you can go
through the examples,
and that'll probably help. Yeah.
With the examples, I think it will be actually easier to understand.
Okay.
Already this kind of example, yeah, please ask any question. I think you're muted.
Oh,
Okay.
sorry. I want to quickly follow up on the question in terms of like how you translate the like non-convex problem to kind of to a integer convex programming problem. Do you have any assumptions in terms of like why you can achieve this convex relaxation?
This exact reformulation of the bilinear constraints?
A few slides earlier, my understanding is more like you maybe one more slides before. Oh yeah, here. Yep. So my understanding is basically you treat the kind of like now before it's like you have to you're given like a subgraph and you want to optimize over a specific subgraph or subnetwork. And then you can kind of like reformulate this in terms of you only have a binary variable y. I was wondering specifically, like, if I have some specific descriptions of, say, my subnetwork H, such that, for example, it only allows, say, like, say, graph distance of, like, basically, like, passes of distance less than p, or kind of like you have to be a circle or something like a traveling salesman problem. Do we still have the convex relaxation?
Yeah, essentially, you would encode that in this polytope y. For example, a polytope y is different for the shortest path from the traveling salesman from the spanning tree. Anything that you encode can encode to through linear inequalities, it'd be fine. For example, if you want to encode that a path has at most 10 edges, you can add to your polytope y the constraint that the sum of the binaries of all the edges is at most 10. That could be encoded in this polytope y, and then we automatically take care of that. We actually leverage that in our mixed integer reformulation. It's going to be provided to us as a description in the polytope y. So you can either give us, I maybe describe this also later, but you can either provide us, ask us to solve a well-known problem over a GCS, and we will do everything automatically, like the shortest path, minimum spanning tree, etc. Or you can ask us to solve kind of a custom problem for which you have to give us the constraints on the binary variables that you want to be satisfied, and then we use those constraints. We try to translate them into a mixed integer convex program for the GCS version.
I see. Thank you.
You're welcome. Is there another question? Maybe if it's quick, or otherwise I don't know how much time I have, but yeah, please go ahead. Okay, I think there was another question. Anyhow, I'll go through the examples then. So let me start with something relatively simple and straightforward to understand. In this case, we have a bunch of islands, an archipelago, and we have an helicopter that is powered by solar energy, and we wanted to fly from this island to this top right island. And the goal is to arrive to the goal island in minimum time. So as the helicopter is flying, the battery kind of drops at a certain rate. You see here at the bottom, we have the battery level as a function of time. Then the helicopter can stop on an island, and the battery can be recharged by the sun. Then the helicopter flies again, and then it has to stop again on an island, and so on. We can formulate this problem as the shortest path problem in GCS. We have one vertex for every island. The variables attached to every vertex, the continuous variables, are the landing position in case we decide to take a recharging break on a certain island, and the battery levels before and after the recharging break. Then we can use the vertex constraints to relate the battery levels to the recharge time. There is kind of a constant factor in there. And then we can say that every time that we visit an island, we pay a price which is equal to the recharging time, which is a function of the battery levels through this coefficient that relates the battery increase and the recharging time. So this is essentially the convex program associated to every vertex. And then on every edge, we do something similar. We have an edge between every two islands that are close enough, and the constraints link the time that you fly with the battery consumption and the positions of takeoff and landing, etc., etc. And then you pay a price, which is a function of these variables. In particular, it's the flight time, which is related to takeoff and landing position, and you can reconstruct the flight time from takeoff and landing position given the speed of the helicopter. So this can be formulated as a shortest path problem in GCS. Imagine if you had to formulate this directly as a mixed integer program, it would take much more than just this kind of modeling exercise. Then you can automatically run our solutions. The optimal flight time is about little more than 30 seconds. The mixed integer solver in this case is solving 24 seconds, which is not very fast. The reason is that this is a mixed integer second order cone problem, and solvers are not very efficient for these problems yet, but they can solve them to global optimality. So in 24 seconds, you get the best possible path through this archipelago. But the cool thing is that if you just solve the convex relaxation, which can be done in a few tenths of a second, you get essentially 99+% there. So the convex relaxation in this case is a very good approximation. So the entire problem is almost essentially solved through a single shot convex program. This is the profile of the solver. You see that the convex relaxation is this lower bound on the optimal value that starts very close, not that the y-axis has a very small range. Then a little bit of effort is needed to find a feasible solution and then to prove global optimality. But you were essentially there from the beginning. Other simple problems that can be formulated in this form, here are a variety. Let me just pick one for simplicity. This one is a cool one, I think. We have a school bus that needs to find a way through a city that looks like Manhattan, like, every distance is measured in the Manhattan distance. So you want to find a tour for the bus, the school bus, to go and pick up all the kids, but the kids are also allowed to move in order to reduce the total time of the ride. So we allow the kids to move, for example, 3 blocks to go in the direction of the bus, and this is the optimal bus tour that we get. You can think of a variation of this being useful, for example, for Uber or Lyft, where on the app they can tell the passenger, oh, you can come 3 blocks in my direction, and this is going to make your ride cheaper. So this is naturally formulated as a traveling salesman problem in GCS, where every kid is a vertex. The decision variables are where is going to be the pickup point for every kid, and then you have standard kind of TSP formulations. Here, the distance is measured again in the L infinity distance. We discussed this problem before. This is kind of a camera positioning problem with many rooms. You want to install a camera in every room for a kind of surveillance purpose, and you have the constraint that every camera needs to be visible from at least another camera in case there is kind of a sabotage, and this is formulated as a minimum spanning tree in GCS. Anyways, you can come up with complicated problems and formulate them pretty easily as GCS problems, and then use our techniques to solve them to global optimality. This, if time allows, I would like to present this and then maybe a quick example of the code. This might clarify one of the questions that came up before, how you define your convex functions. Let's take, for example, a motion planning problem where we want to find the shortest possible trajectory that goes from the source point to the target point and avoids 2 obstacles in red. We will formulate this as a shortest path problem in GCS. The first step is that we decompose the free space into a collection of convex sets. This step can be complicated, but we have developed good tools for this. So imagine you have this decomposition of the free space into convex sets. Now there is a natural graph that you can associate to this decomposition, where you have one vertex for every cell, for every convex set in this decomposition, and you add an edge between every 2 convex sets that intersect. For example, the set labeled with 1 and the one with 3 intersect, so we have an edge between them. We have a vertex representing the source that is injected in the first region because the source is in the first region, and we have a vertex representing the target in the 5th region. So we want to find the shortest path between the source and the target. The continuous variables here, we parameterize the trajectory within each one of these convex sets using a line segment. So we parameterize it with 2 points. If the 2 points are in the convex set, then the whole line is in the whole line segment is in the convex set. So these are our continuous variables, 2 points for every vertex. As an edge constraint, we can say that when you move from one convex set to the other, then the final point in the first convex set needs to be equal to the initial point of the next trajectory segment so that you get continuity of the overall trajectory. And then every time you visit a region or a convex set or a particular vertex in the graph, you pay a price that is equal to the distance of the two points that you have used to parameterize your trajectory there, which is actually equal to the trajectory length. So in this case, the objective function f that we were discussing before is actually the length, the sum of the lengths of each one of these segments. When you minimize the overall objective, you're looking for a path that goes from the initial point to the final point and has minimum total length. And you can extend this idea using polynomials and Bezier curves to design smooth trajectories. I'll go a bit quickly since we're late. We applied these techniques, for example, to something that to us at least looked like a very non-convex optimization problem, finding the minimum length path through a maze. So here we are looking for an actual continuous trajectory that traverses a maze in minimum distance. Again, we have a vertex for every little square in this maze, and edges connect two neighboring cells that are not divided by a wall. We can find a minimum length trajectory, also some minimum time trajectory with some continuous constraints. And the good news is that is actually for these problems, both these problems, the convex relaxation is exact. So although the problem looks extremely non-convex with many local minima, when we formulate it as a GCS, when we look it from the point of view of our binary variables y, actually this problem becomes all of a sudden convex, and it can be solved through a single-shot convex optimization problem. We have tested our motion planning techniques on a variety of examples. Here you had UAVs. The main take-home message was that the relaxation, the gap between the relaxation and the original MICP was very low for most of these randomly generated instances. And with a little bit of extra rounding on top of that, most of the times you recover the global minimum, the globally optimal trajectory, just with the effort of solving a convex program. We have developed approximate versions of these motion planning problems that can scale to very large problems. Here we are designing a trajectory, a minimum snap trajectory around tens of thousands of obstacles, and this can be done very quickly if we are willing to sacrifice a bit of optimality, but preserving still the algorithmic completeness. We have tested our GCS motion planning techniques against existing methods for motion planning. Here we have the PRM. The high-level message, again, is that we find better trajectories, so shorter trajectories, more efficient trajectories, in actually also a fraction of the time. And our techniques can scale to higher dimensional problems than provided that you can decompose the complex configuration space of these robots, which is itself a complicated problem. But again, we have worked hard on developing techniques for these convex decompositions. Our techniques can also scale to these high dimensional problems. In this case, you have two KUKA arms, so 14-dimensional configuration space. All these motions are generated only by solving the convex relaxation of the shortest path problem in GCS. And then also the timing, this particular one, also the timing and the order of the pick and place is optimized. Let me maybe just give a high-level idea here. This is a non-prehensile manipulation. Again, we can formulate the problem of a pusher slider system. We want to move the object to the desired location by formulating it as the shortest path in GCS, where different paths through the graph represent different contact sequences, and within each fixed contact mode, we have a semi-definite approximation, a convex approximation of the dynamics of the pushing dynamics, and then again through a single convex program, essentially you can optimize. It's actually a mixed integer convex program, but the convex relaxation is again very tight. So through a single convex program, you can optimize these complex behaviors. The techniques that I've described today have been also used a bit in industry. We were interacting with a startup that was doing food preparation, and they moved from PRM actually to GCS, and they were very happy about the trajectories generated. And their goal was using these two robots to assemble bowls of food that were the ingredients of which were provided by the user. I think now they've been acquired by Sony. I've worked myself at Amazon, and we have developed variants of these techniques that hopefully will make to production with the new generation of the Amazon robots. Joel, if I can, maybe I'm out of time, but if I can just take 1 minute, I will present these. Otherwise, I'm happy to stop here.
Sure. Feel free to present.
Okay, it's just going to take 1 minute. I just wanted to show you that, although maybe some of the math in this presentation was a bit scary, coding these problems is extremely easy. This is a super quick tutorial on the code that I've developed. Let's say that you want to find the shortest path in this GCS going from the bottom left circle to the top right. Every continuous variable needs to be selected within the corresponding circle, and the only price we pay is when we move from one circle to the other, we pay a price that is equal to the distance of the two points that we are connecting. So we are looking for the shortest Euclidean sequence of steps that can take us from the bottom left to the top right while following the arrows in the graph. To install GCSOPT, you just pip install it. Then you can import GCSOPT as shown here, and you should also import CVXPy, which is the language that we use to define complex sets and functions. This is just a parameter, the side of the grid, which is 3, and the radius of the circle, 0.3. We can initialize an empty directed graph of convex sets as follows. Then we can add the vertices by iterating over this grid for all I in the length of the grid. For all j, we define the center of every circle. We add the vertex to the GCS, and we name it just after its center. We add continuous variables to every vertex, and we add constraints that the norm 2 of the continuous variables minus the center must be lower or equal than the radius. This forces all our decision variables to be within the corresponding circles. Then we can add edges. We again iterate through the grid. We check if we can connect to something on the right or on the top, and if we do, we retrieve the vertices, we add an edge, we retrieve the variables, and we add the cost that is the norm 2 of the distance between the points, and then we can just solve the shortest path. After retrieving the source vertex and the target vertex using their names, we can just call graph solve shortest path from source to target, and this automatically constructs the mixed integer program, solves it, and populates the GCS with the problem solution. For example, if you want to know the optimal value of the variable paired with the source, this point over here in the bottom left, you can just say, first you retrieve the variable, xs is the first variable associated with the vertex s, and then you just print its value as follows. And if you want to generate this image on the left, you just run these 3 lines of code, and this is actually how this image is generated. Additional considerations on GCSOPT, it has this basic interface to define graphs, as we have shown. The cool thing is that it uses CVXPy to define all the convex functions and sets. So anything that you can do in CVXPy, all the crazy log determinants that you can come up with, they can be used in GCSOPT automatically. And then we also use CVXPy to communicate with the solvers. So any solver that is supported in CVXPy, which is a much larger community, will automatically be supported by us. Unfortunately, there aren't very good free solvers for mixed integer convex programming yet. But if you are in academia, you can use Gurobi, Mosaic, or Cplex. They have free academic licenses, so that allows you to solve very big GCS problems. If you're not in academia, you can still work on the idea of solving only the convex relaxation and then use some rounding to find approximate solutions. Thank you very much. Sorry for running long. This is the list of papers that I've discussed today. Some of them, please feel free to ask me more questions or send me emails if you're interested.
Thank you.
Thank you, Tobia, for the wonderful talk. So I guess, unfortunately, Jolly has to leave a few minutes early because he has to run for another seminar. So I will be in charge of the Q&A sessions. And everyone who is interested in the talk and have follow-up questions, feel free to just unmute yourself. I guess we can take one quick questions due to the time.
I just was curious where the recording would be for the talk. I'd like to rewatch some of it.
I guess on YouTube.
Yes, the recording will be on our YouTube channel.
Okay, great. Thank you so much.
Sorry, can I just go with a quick question? For the rounding part, it's just more like a trivial rounding, or is any particular cures for the rounding after the convex relaxation?
Yeah, so let me try to understand the question. So you're asking if the rounding part, if you just want to do convex relaxation plus rounding, whether you can apply any trivial rounding or if you need to come up with something more sophisticated?
Yeah, I'm just wondering, like, is there any more specific rounding cures that you have for your convex relaxation?
Yeah, so the GCSOPT allows you to essentially provide a rounding function. So it can solve the convex relaxation, and if you provide the rounding function, then it can use that. The rounding function needs to depend on the problem. So for example, the naive rounding of just saying if a variable is close to 0, set it to 0. If a binary variable is close to 0, set it to 0. If it's close to 1, set it to 1. That's not going to work for most problems, right? It's too simple. And for example, when you have the convex relaxation of a shortest path, it might round to something that is not a path at all. So you need to be the rounding technique requires a bit more work. For example, for the shortest path, what you can do is you start from the source, and then you construct a path iteratively by taking every time the edge with the highest binary, with the largest binary. So that's a simple rounding technique that applies to the shortest path. You can modify it for the traveling salesman, for example. That's another, problem that meets simple rounding strategies. But yes, the rounding strategy requires some thought and depends on the specific GCS problem, the specific combinatorial optimization problem you're solving.
Thank you so much.
You're welcome.
Quick clarification question. So are these problems always solved as convex relaxations, or would you ever solve it as like the actual mixed integer program?
Yeah, thank you for the clarification. I guess it wasn't super clear, but it really depends on the problem. Like, okay, you can always solve them as mixed integer convex programs, right? For some problems, for example, the shortest path, the original integer convex programming formulation is extremely good, and that's typically inherited by our mixed integer convex program. That means that the relaxation will most of the times get you 90+% there. So for the shortest path, and if your problem has a particular structure for which, for example, the rounding will always succeed, or this specific special properties, then you might be happy with just saying, I'll just solve the convex relaxation and I'll do some rounding, especially if there is some mathematical reason why that is a good idea. In general, though, you want to solve the mixed integer program. For example, for the TSP, the problem can be computationally hard. The convex relaxation is not as good as the shortest path for the shortest path, so rounding might not always work as efficient. But it's problem specific.
Okay, thank you.
But yeah, the mixed integer approach always works. For some cases, you might be able to take the result home with less.
Okay, and then another quick question: like when these, assuming maybe you don't have a convex, like maybe your FE or FE is non-convex, is it like are you still, does this framework still work to solve like non-convex problems for like local optima, or is it like specifically fit for convex problems?
Yeah, so that's another great question. So what happens in that case is that the code right now would not work, would complain, because I'm using CVXPy, and CVXPy only accepts convex things. The math, though, could work, especially for the shortest path. It's kind of technical, the reason, but you don't want to end up with a mixed integer non-convex problem, because there are essentially no solvers for those. but if you can turn the problem with non-convex objective functions into a smooth non-convex program, as you actually can, and I'm happy to give more details maybe offline, for the shortest path, then you could think of just using IP-opt or SNOP to solve these problems to local optimality, the GCS version, with non-convex costs and constraints. In case of a shortest path, that's possible. And this leverages the fact that the convex relaxation of the original shortest path problem is exact. But yeah, you can. It would require some thought and new code, essentially.
Okay, thank you.
You're welcome.
Thanks everyone for the question, and thank you so much for the amazing talk, Tobia. So I guess due to time constraints, we'll leave all the other questions offline.
Yeah, please feel free to send me an email. And thank you very much for inviting me.
Thank you for giving a talk. All right.
See you, everyone.
See you, everyone.
Thank you.